Welcome back, physics friends. We're now going to dive even deeper into the three consequences of relativity. Last time we focused on the rear clock set ahead, or also known as the relativity of simultaneity. That was the first of three consequences of relativity. Today we're going to focus on time dilation, and our mnemonic to remember time dilation is that we're going to say a moving clock ticks less, and that's implying ticking less than a clock at rest. Okay, and remember, all of these three consequences of relativity come out of the two postulates. The principle of relativity, namely that we should be able to do physics or analyze a problem in any inertial frame, and we should get equivalent results. There's no preferred reference frame. That's the first postulate. And the second is that the speed of light is the same for all observers, independent of the speed of the observer and independent of the speed of the source of that light. So we're going to make use of those two postulates to uncover time dilation. And it's actually kind of a fun thought experiment that we can do. And it doesn't take much in the way of mathematics. We can quickly see qualitatively that a moving clock will tick less than a clock that's at rest. And then to find the quantitative explanation for it, in other words, how much less does the moving clock tick, then we need to do some math. And the math we're going to rely on is the Pythagorean theorem, that the length of the hypotenuse is the square root of the sum of the squares of the other two sides of the triangle. And that's really all we need in order to derive this very interesting result. Now, before we dive into time dilation, I want to point out something that's really important. Both consequence number one, RCA, and consequence number two, time dilation, have to do with clocks. The first point, RCA, has to do with the reading on two different clocks that are at different positions in a moving frame. And the second, time dilation, has to do with the rate that clocks tick. So I want to draw a little diagram and make sure we're clear on the distinction between the two. And after we're clear on that distinction, we will derive time dilation. So let's refresh our memory a little bit on the rear clock set ahead. So our setup here is that we have Bob, who's standing at rest on the ground, and we have Alice, who's standing at rest on, let's say, a space platform. So we have this platform, and on either end of the platform, we have a clock, okay? Now in Bob's frame, right, so I got to identify that this is in Bob's frame. Always label your frames. In Bob's frame, Bob is at rest, and the platform is moving to the right at some speed v. Because these two clocks are not at the same location, in other words, this front clock is going to reach Bob before the rear one does, RCA, or rear clock ahead, tells us that the rear clock is going to read a number bigger than the front clock by an amount L naught V squared, L naught V over C squared. Okay. So let's say, for sake of argument, that the reading on this front clock, is 0. Okay, that means the reading on the back clock is 0 plus L naught V over C squared. Okay, so whatever the front clock reads, the back clock reads more, a higher number by L naught V over C squared. So if we let some time evolve and we draw the picture again at some time later, let's see what happens. Okay, so as time has gone on, we notice that Bob has not moved because we are in Bob's frame, and yet Alice and the platform have moved to the right. Some time has elapsed, which means the front clock now reads some other number. So let's say 2 ticks of the clock have happened. So now the front clock reads 2, okay? Well, how about the back clock? Have 2 ticks also happened on the back clock? Yes, in fact, 2 ticks have happened on the back clock, but the back clock is still always going to be ahead of the front clock by that same amount, L naught V over C squared. Okay, so if the front reads 0, the back reads 0 plus L naught V over C squared. If the front reads 2, the back reads 2 plus L naught V over C squared. No matter what the front reads, the back is always going to be bigger by the same amount. In order for that to happen, though, notice that there's the same number of ticks between the front clock in the two pictures. So in the first picture, it reads 0. In the second, it reads 2. That's 2 ticks. The back clock has the same situation. In the first picture, it reads 0 plus L naught V over C squared. In the second, it reads 2 plus L naught V over C squared. Both of these clocks have ticked twice. Okay, so to go from the first picture to the second, that's 2 ticks of the clock. And that's the same for the front and back clocks. Okay, so although the clocks have different readings on them, they are ticking at the same rate as each other. Okay, that's RCA. Time dilation is saying something else. There's also another time-related effect of relativity, and that is that the rate that the moving clock ticks, these 2 ticks, is different than the number of ticks on Bob's clock. Okay, so to make up a number here, let's say that Bob has a clock, and that clock is at rest in his frame. Okay, and we'll start that clock at 0. Okay. And if the moving clock has ticked twice, it went from 0 to 2, and moving clocks tick less, and we'll see why in a minute, that means we must have more than 2 ticks on Bob's clock. More than 2 ticks. So I'm going to make up a number. I'll say 3. Is it always 3? No, it depends on the speed of the moving platform. Okay? But the key idea is that Bob's clock ticks more than Alice's clock because in this frame, Bob's clock is at rest and Alice's clock is moving. So RCA tells us how 2 clocks in the same frame are related to each other in terms of their reading. Time dilation tells us about the elapsed time in one clock in one frame compared to the elapsed time of a clock in a moving frame. Okay, so we're comparing, time dilation compares 2 different clocks that are in different frames, and RCA compares 2 clocks that are in the same frame. Okay, if this still seems a little bit fuzzy or unclear, that's okay. We're going to talk much more, we're going to talk about time dilation first and derive it, and then we'll revisit this distinction in the future. Okay, if we're going to talk about time and elapsed time and time ticked off as being different in different frames, we need a way to measure time and time elapsed and time ticked off. So we're going to use something called the light clock for that purpose. Okay, and so in all of our thought experiments for time dilation, we're going to make use of this device called a light clock. And a light clock is a device that emits light from the bottom. Okay, so imagine a box that has a source of light down here, and then some distance above it, we're going to put a mirror, and we're going to have the photon launch down here. It's going to travel up, it's going to reflect up here, then it's going to bounce back down, and then the photon will return. Okay, and the process will repeat. So each round trip is 1 tick. Okay. And every clock or stopwatch needs a way to tell the user how much time has elapsed. So we'll use our little diamond symbol down here that keeps track of how many ticks there have been. Okay, so 1 round trip equals 1 tick. So when this first launches, when the photon is first launched, this will read 0. As the photon rises, the reading is still 0. At the reflection point, the reading is still 0. On the return, the reading then changes to 1. Okay, so after 1 round trip, now this reading becomes 1, and that's 1 tick, and so on, and the process repeats. Now, if we're clever, we can design the clock in such a way that the number of ticks is equal to the number of nanoseconds, right? So we know that the speed of light is 1 foot per nanosecond. Okay, so if we make the round trip length of equal to 1 foot, then 1 round trip will take 1 nanosecond, and each tick corresponds to a nanosecond. So in order to do that, we would make the height of this clock be half of 1 foot, so that the round trip is 1 foot. Okay, and now we've constructed a device where we've constructed a device that keeps track of time in nanoseconds. Okay. For the purposes of deriving time dilation, we don't actually need to know that we don't need to construct a clock that gives nanoseconds of reading. We just got to keep track of ticks, okay? So for our purposes, we're actually going to, instead of calling the height half a foot, we're just going to call the height h. So we don't really, we're not too concerned with a number for the height, but we do need to give the height a label so that we can refer to it. So we'll use the label h. So now imagine that this light clock is just sitting at rest on a table in front of you, and you're watching the photon and you're monitoring its path. Okay, well, the photon's going to go straight up, hit the mirror, reflect back straight down, and repeat that process. Up, down, straight up, straight down every time. So it's a straight up, down path, nothing complicated. Now, what happens, though, if the clock were moving across your field of view, say from left to right? Well, instead of going straight up and down, you can convince yourself, I think, that you would watch the light go up and to the right and down and to the left, right? Because the clock itself is moving left to right, and the photon always stays within the clock. So if the clock is moving to the right, the photon also has to move to the right to keep pace with the clock. Okay, so let's actually set up a problem now, draw it out, and work through it. And we're going to, once again, look at a clock ticking in two different frames of reference. We're going to have Bob on the ground at rest relative to the ground, and we're going to have Alice in a rocket ship, and there's going to be a clock for Bob and a clock on the rocket ship for Alice. So here we go. We have a drawing made in Bob's frame in which Bob is at rest on the ground along with his clock. Okay. Alice, however, is on a rocket ship, and that rocket ship is moving at high speed to the right. We have a light clock for Alice that's at rest in her frame, and we have a light clock for Bob that's at rest in his frame. So we can say that in Bob's frame, Bob's clock is at rest, and the reading on that clock we'll call delta t Bob, meaning the change in time as measured on Bob's clock from t equals 0 until some later time. Similarly, in Bob's frame, again in this diagram, Alice's clock is moving, and we're going to call its reading delta t Alice. Our main result that we're going to derive next is to show that delta t Bob, the amount of time ticked off on Bob's clock, is bigger than delta t Alice, the number of ticks of Alice's clock, and it's bigger. Delta t Bob is bigger than delta t Alice by a factor of gamma, where gamma is our shorthand notation for this quantity 1 over the square root of 1 minus v squared over c squared, and this v is the velocity of Alice's clock. So that's our main result, and what we're going to do next is derive that result. Before we get into the nitty-gritty and the derivation and the details, we're going to make a qualitative argument that makes it clear that it will take more time for Alice's clock to make one round trip than it will for Bob's clock to take one round trip, as measured in Bob's frame. So let's do that next. Okay, so here we are. We're going to show qualitatively that the moving clock ticks less than a clock that's at rest. And we're going to do so by looking in Bob's frame once again. And we have Alice's clock. Remember, that's on a rocket. For the simplicity of the drawing, I'm going to not draw the rocket in every time. I'm just going to draw her clock and indicate that it's moving with a blue arrow. Over here we have Bob, who's at rest in Bob's frame. Bob has his own clock, and his own clock is at rest in his frame. So remember that for Bob, his photon on his clock goes straight up, reflects, and comes straight down. So it's an up-down motion. But what about for Alice's clock? Well, let's say in this first drawing here, Alice's clock is just about to launch the photon. That's the purple dot, okay? And that photon is going to travel towards the mirror on the other side of the clock. But don't forget, the clock is moving. Ooh, that doesn't sound good. Something's wrong in Childland up there. So the clock is shifted over to the right, okay? And let's say that this second picture represents the instant of time that the photon is hitting the mirror. So I'm going to put my photon hitting the mirror up there. And then sometime later, wait a little longer, and the clock has moved over to the right some more, because remember, it's continuing to move to the right. It's on the rocket. And so we can indicate that with our velocity arrows. And let's say for this third picture, well, now the photon has just returned home. to where it was launched from. So these three pictures represent three snapshots of one round trip. We start with the launch, we see the reflection, and then we have the return back to the original position. Well, remember for Bob, where the clock's at rest, the light just goes straight up and straight down. But that's not going to be true for Alice's clock, right? Alice's clock, which is moving through Bob's frame, the photon starts down here, and then halfway through it's up and to the right. So the path that the photon takes is up and to the right, and then down and to the left. So instead of taking this straight up, straight down path, it takes a triangular path, okay? And how does the triangular path length compared to the straight up, straight down path length? Well, we know it's going to be longer, right? The hypotenuse of a triangle is longer than the side, either of the other two sides of that triangle. So we know this purple line for Alice's clock is going to be longer than the purple line for Bob's clock. Okay, that's step one, is that Alice's photon has to travel further than Bob's photon. Okay. Step two is we know that all photons travel at the same speed. So then we say, okay, well, if distance equals speed times time, then time is distance divided by speed. If I have two photons that are traveling at the same speed, but one has to travel a larger distance, then it's going to take a longer time to do so. So that's the main argument, is that the clock that's moving, that photon has to take a longer path to make one round trip, and if the path is longer, it's going to take a larger amount of time to make the round trip. Whereas in Bob's frame, all it has to do is to go up and down. That's a shorter trip, so that will happen more quickly. So if Bob's round trips are more rapid, then his clock will tick more times for every one tick of Alice's clock. So the summary statement here is that a moving clock ticks less. Okay, moving clocks tick less. And tick less than what? Well, than a clock at rest. Okay. So if we were to put names to this, in Bob's frame, right, Bob's clock is at rest. So Bob's clock is the clock at rest, Alice's clock is the moving clock. So in this frame, Alice's clock ticks less than Bob's clock. However, you could analyze the situation from Alice's frame. And in Alice's frame, her clock would be at rest and Bob's would be moving. And Alice would say that her clock is at rest and therefore ticks more than Bob's clock. So Alice would say Bob's clock is moving and therefore Bob's clock ticks less than Alice's clock. So how is it that Alice thinks her clock ticks more than Bob's and Bob thinks his clock ticks more than Alice's? That seems to be a contradiction. In fact, that is the content of relativity. And we're going to explore the implications of this apparent conflict in the subsequent classes. For now, however, let's get quantitative, right? At this point, we can say that this triangular path is longer than the straight up, straight down path. But how much longer, and therefore how many more ticks will Bob's clock have than Alice's clock? For that, we're going to have to do some Pythagorean theorem, which you can imagine because we're comparing the length of one side of a triangle to the length of the hypotenuse. Okay, so I've copied over the diagram from the previous page showing the purple trajectories, the triangular shape for Alice's clock moving through Bob's frame, and the up-down shape for Bob's clock in his own frame. So I'll redraw that big purple triangle shape a little bit bigger so that we can annotate it. Okay. And we want to identify a right triangle. And we know the height, we gave that a name before. We said the clock was a length h tall, so we can label that. And then we'd like to know the length of the base. And remember, our goal is to find the hypotenuse length. So we have this right triangle. What do we know about this base? What do we know about this base? Well, we know that this is happening in Bob's frame, and we know that Alice's clock is moving at speed v. So this distance, the horizontal distance covered by the photon, can be found by remembering that distance traveled is equal to speed times elapsed time. So the speed is equal to v, that's the speed that the clock is moving. Right? And then the elapsed time is delta t, but we have to be careful. Is it delta t Alice or is it delta t Bob? Well, remember, we're in Bob's frame. So the elapsed time in Bob's frame is always going to be the time ticked off on a clock that's at rest in the frame. So this is going to be delta t Bob. So delta t Bob, remember, is the time measured by Bob's clock. Okay, so now we're in really good shape because we want to know the geometry of this right triangle, which is half, the base of that triangle is half of the long base. So we can just write that the base of this right triangle is v delta t Bob, all divided by 2. Okay, and our goal, right, is to figure out what is this path length. Actually, the full path length, which is twice of one hypotenuse. And we know the other two sides of this triangle, so we can use Pythagorean theorem to write the length of the hypotenuse. And the length of the hypotenuse is the square root of the sum of the squares of the other two sides. Like so. Okay, so it's a bit of a mouthful, but it's the square root of h squared plus v delta t Bob over 2 quantity squared. So now we have what we need to proceed. We can say that in Bob's frame, Alice's light clock photon travels a path that's this solid purple line, and that distance is going to be equal to c delta t Bob, because the distance traveled by a photon traveling in speed c is always going to be speed times the elapsed time. But we have another way to write that distance. Right? We can write that distance as 2 times this big square root term. Okay, so on the left-hand side of this equation, we bring in the hypotenuse length. We double it because the light has to travel 2 hypotenuses, and that's got to be equal to c delta t Bob. Okay, we've done the hard part in terms of the physics, identifying how to write the distance traveled by the photon. Now we have to turn the crank, and our goal here is going to be to solve this equation for delta t Bob. So we have it on both sides. We're going to have to square things and do some rearranging. So there's a bit of algebra coming, but we've done the hard part. We've done the physics. Now we have to turn the algebra crank, and we'll do that on the next page. Okay, so we have everything we need, and we're just going to proceed by turning the math crank. The first thing we're going to do is actually bring this factor of 2 into the square root, and we know that 2 is the square root of 4. So we can bring a 4 under the square root and write this whole thing on the right-hand side as 4 times the quantity of what's inside. Okay, and I hope you'll let me abbreviate Bob with just a B. Just saves me some writing and some time. Okay, good. And then I'm going to distribute that 4 through, okay? So I have the square root of 4h squared, okay? And that 4 is also going to multiply the v delta t over 2 quantity squared. So I have a v squared and a delta tb squared. And that's over 2 squared. 2 squared is 4, but I'm multiplying it by 4. So 4 divided by 4 is 1, and that term is finished now. On the left-hand side, I still have c delta t Bob. And now I'm going to square both sides. Okay, so I'll take this side and square it, and I'll take this side and square it, and I'll write the result. We got c squared delta t Bob squared is equal to 4h squared plus v squared delta t Bob squared. Okay. And this is one of those things where the equations start to look worse before they start to look better. We're actually headed towards a really nice, clean result. We're almost there, but not quite. So we have one more step. Well, a few more steps, not just one. We'll bring this v squared delta tb squared to the left-hand side. So we have c delta t squared minus v squared delta t bob squared, like so. And on the right-hand side, we're just left with the 4h squared. Okay. The next thing we're going to do is multiply through by 1 over c squared. Okay. And so that's going to be a c squared over c squared, which just gives us 1. So the first term is just delta TB quantity squared. Then the second term here is going to be a v squared divided by c squared. Also multiplying delta TB squared. And then on the final term, the term on the right-hand side, is 4h squared over c squared. Okay, now we're really close. We can see on the left-hand side we have two terms that share this delta TB quantity squared. So we can factor that out. Delta TB squared. That's going to multiply 1 minus v squared over c squared. And on the right-hand side, we'll just leave it alone and recopy that term. Okay. So remember, we're trying to solve for delta t. Well, right now we have delta t squared. So let's square root both sides. Okay. So we'll square root the left side and square root the right side. And that will bring us up to the top of this right-hand side. So we'll have delta TB no longer squared. And then we're going to square root the 1 minus v squared over c squared. And then we square root 4h squared over c squared, and we get 2h over c. Okay. Now, we're going to pause here, and we have to do some thinking, some physicsy thinking. 2h over c. What is 2h over c? Let's think about that for a minute. Remember, we've chose delta TB to be the time that Bob says it takes for Alice's light clock to make one round trip, to tick once, okay? Now in Alice's frame, her light clock, the photon goes straight up and straight down because her light clock is at rest in her frame. And if you remember, the light clock, we said, had a height of h, and so one round trip is 2h in terms of length. So the round trip distance is equal to 2h. This numerator on the right-hand side is the round trip distance for Alice in her frame. Okay, straight up, straight down, that's her clock tick. And if we take a distance and we divide it by a speed, we get a time. Okay, so this 2h over c squared is actually the time it takes as measured by Alice for her clock to tick once. And we said that that was delta t Alice. So now we have an equation where on the left-hand side we have terms involving delta t Bob. And on the right-hand side we have delta t Alice. So this equation helps us relate the time measured by Bob and the time measured by Alice. And we see they're not equal. That's the first thing to notice, okay? So delta t Bob is not the same as delta t Alice. They disagree on how long it takes Alice's clock to tick once. In other words, in the time it takes Alice's clock to tick once, Bob's clock has ticked more than once. Okay? So remember, we're trying to solve for delta TB. So we can take one final step here and say delta TB is equal to 1 divided by this square root term, all multiplying delta TA. And that's it. That's what we set out to do. Okay? Except this term, 1 over the square root of 1 minus v squared over c squared, it's kind of a lot to write all the time, and it shows up all the time in relativity. And so we're going to define a symbol that we call gamma, the Greek letter gamma, and we're going to define that to be 1 over the square root of 1 minus v squared over c squared, just as a shorthand notation. And so what that allows us to do is to say that delta TB is equal to gamma times delta TA. So these two boxed equations are identical. We've just introduced a symbol to make it shorter, that's all. So the bottom line is that Bob and Alice disagree on how long it takes Alice's clock to make one round trip. And what we'll see in the next slide is that gamma is always bigger than 1. And so if gamma is always bigger than 1, then delta TB will be bigger than delta TA because we're multiplying delta TA by a number bigger than 1. Let's take a few minutes to digest what we just discovered. So to draw things in a more cleaned up way, we have Alice in the rocket moving to the right in Bob's frame, Bob at rest with a clock at rest. And what we said is that the time that Bob measures for one round trip of Alice's clock that's going to be larger than the time that Alice measures for that round trip. Okay. In other words, the moving clock ticks less than the stationary clock. Now, because of the principle of relativity, we could flip things around and study the situation from from Alice's frame. And in Alice's frame, her clock would be at rest, and Bob's clock would be moving. Okay, and Alice would say, "Oh, Bob's clock is moving, therefore it ticks less than my clock." And the logic would be the same, and the derivation would be the same, including the Pythagorean theorem and so on. So we have to be careful when we look at this equation. It's not that Bob's clock is always going to tick more than Alice's clock. The important piece here is not which person is Bob and which person Alice. The important thing is which clock is at rest in this frame and which clock is moving in this frame. So the general way to write this equation is not in terms of Bob and Alice, but rather delta T at rest for a clock at rest is equal to gamma times delta T on a clock that's moving. This is the time dilation equation. Okay. And remember, the mnemonic for this is that a moving clock ticks less. And that's equivalent to saying delta T moving is less than delta T at rest, because gamma is bigger than 1. We'll take a deep breath at this point and just reflect on what we've done. We've used the fact that the speed of light is constant in all reference frames, and we showed that because the moving clock forces the photon to take a triangular path instead of a straight up down path, it's going to take longer to complete that one tick. And what we had at the end of the day, the consequence of that is that the time elapsed on a clock at rest is more than the time ticked off on a moving clock. We're going to dive deeper into this gamma factor in the next video. For now, all we need to know is that gamma is bigger than 1. So delta T at rest is larger than delta T moving. So hang on and join us for the next video, and we'll explore how this gamma factor depends on velocity, and we'll plot out the shape of this gamma curve as a function of velocity. We'll see you next time.